Good afternoon, everyone, and welcome to our discussion on the quantum internet from myth to reality. We've got some really exciting panelists here this afternoon. And just to kick off our discussion, I'd very much like if I could ask you to vote. You can see there's a little poll that should have popped up on your screen, which says, do you expect the Smart Internet Lab conference in 2031 to be delivered over the quantum internet? I'd like you to vote in that, please. Fantastic. Thank you very much. In that case, I'd like to kick off by introducing you to the panel. My name is Edmund. I'm a lecturer here at the University of Bristol in quantum communication technologies. And our panel discussion this afternoon is focused on the quantum internet, discussing from myth to reality. And I'd like to kick off by sending some apologies from one of our attendees. We heard from, fortunately, Andrew Lord is not going to be able to join us today, but we've got a very exciting panel and we've got people with very strong opinions about the quantum internet. So I'm hoping we're going to hear some of those and have a really good discussion. Could I ask Annetta, Rebecca, could we move on to the next slide, please? And I'd like to introduce our first panelist, Dr. George Kanellos.
All right. Hello, everyone. I'm George Kanellos. I'm a senior lecturer with the University of Bristol and affiliated with the High Performance Network Group and the Smart Internet Lab. I would like to thank the organizers for inviting us in this very interesting panel discussion on the quantum internet and the potential for that to be deployed in the future. And as an introduction to this, I would like to go into my next slide, which is, if we can move to my next slide. All right, so this is an exercise that we put together with our colleagues in High Performance Network Group and in KETS Lab within the framework of the Quantum Communication Hub. Where we actually try to identify all the technologies that are currently available for quantum communications. So you'll see it's a large variety, huge plethora of technologies spanning from DV-QKD, so discrete variable QKD systems, to continuous variable QKD systems. Then we have the entanglement distribution that starts with obviously using entanglement sources and distributing the entangled photons into the various nodes. And with that, we can address it to perform again QKD, or we can use it for other forms of quantum information exchange, or apply different types of protocols such as the quantum conference key agreement, etc. Which brings us to another consideration, that of application. I'll come back to that in a minute. However, if we have a closer look to the map, we'll see that there are also these red boxes that represent what we call trusted nodes. And because of the restrictions that we currently have on the transmission of the capabilities of the quantum communication technologies available, and the lack of quantum repeaters, or at least reliable deployable quantum repeaters, we have to rely on these concepts of trusted nodes, which is a form of replicating the quantum information and retransmitting it. And then we have another span of classical technologies that are modified and brought into the quantum realm, such as, for example, the quantum reconfigurable blood drop multiplexers, or an elaborate form of switching, of quantum switching. And then, of course, studies or extrapolation of the potential of applying quantum and classical channels into the same medium, if you like, with a optical fiber, with a standard optical fiber being the most common medium used up to date. So we did this exercise not only to identify what are these technologies, but what are their potential applications in terms of physical deployment into the network. And for that, we used our experience from classical networking to rank them into access quantum networks, metro quantum networks, and core quantum networks. They could also, we could also use a different approach and classify them based on the application rather than the reach. But what mainly brings into what mainly this picture brings into perspective is in fact the following questions. So we have all these technologies, but are these competing or should be seen as complementary technologies? Obviously, each own has their own characteristics and their own advantages and disadvantages. But the question that lies within is whether one can expect some interoperability, both in the physical layer, so having these systems transmitted again together, talking one to another, but also on the network layer or on the application layer. For example, if you have different QKD systems that are brought together into a trusted node, and these come with different physical implementations or different protocols, how do you align, for example, on the key management? How do you align on the key exchange? What are the security measures that one has to consider? So interoperability is a major consideration if we want to consider tomorrow's quantum internet becoming a reality. The second aspect of it is, of course, the maturity. In my slide, I put the question around the essential elements, such as the repeaters, when it comes to the communications, quantum memories, when it comes to also some form of quantum processing. But it can also expand to the maturity of the technologies in order to be deployed and provide some actual return on the investment of the research. And I guess that Jake in the next slide can also answer in this potential. A third question mark is around the quantum interconnects in general, and that reflects again on the coexistence potential. So one major question to be asked is whether we will deploy this quantum internet or quantum network as a separate parallel layer, physical layer to the classical infrastructure, or is that going to be embedded on the same infrastructure? And if that's going to be using the same classical optical networking infrastructure, if you like, then how do we deal with the noise and with the impairments that the classical signals have on the quantum communications? Very recently, we've explored the potential for using new fibers and new mediums, such as hollow core fiber, that seem to have a potential to remove all the restrictions in applying quantum signals together with classical, and therefore allow for a seamless or unconditional coexistence between the two. So that again is another consideration. And finally, on the network level, or if you like at the higher levels, it comes again to whether we have a single focus on one application, the QKD, the quantum key distribution, the quantum security being the main application up to date, or other applications such as quantum information exchange for quantum computing, and whether these can be bridged under the same system of network control and orchestration, and whether that can be optimized globally. And of course, if our focus is around the security, the implication that the higher layer have is actually how much trusted are trusted nodes. That has previously been a topic of discussion within the quantum community, but with respect to the physical layer aspect, so how the quantum links can be secured within a trusted node. But once you consider the higher layers of networking, the communication with external controllers, the signals of the received from the controllers, then the question is moved to whether how secure the control and the management of the system is. And with that, I would not like to abuse more of the time from the rest of the panelists. I would like to stop with these provoking questions, and happy to discuss them further later with the panel.
Thank you very much, George. That was fascinating overview. Our next speaker provides us with an industry perspective. We're going to hear from Dr. Jake Kennard from KETS.
Thanks, Edmund. Thanks for the kind introduction. Also, thanks very much for the invite to this panel. I think it's really great to be part of such an interesting set of people talking about a pretty interesting question, I think. So yeah, my name is Jake Kennard. I'm co-founder of KETS Quantum. KETS are a startup based out of some research done in the University of Bristol, really over the last couple of decades. And in particular, we have been focusing on taking quantum safe components, so QKD, QRNG, and shrinking them down to chips that are made in standard telecom foundries. So I just had a few short points that I wanted to make on this kind of overall question of how do we go from taking quantum networks from sort of myth to reality. And I think almost the first interesting question is, what does reality mean? I think it's different for different people. And for me, I think it's about wide scale use. So it's about seeing it to the same level that we see conventional networks today. So that means, yes, very wide scale use and or, very much commercial deployment. So on that, I think I think it's kind of important to acknowledge that we really need to be clear about what it is we're talking about and why we want it. I think there really is quite a large difference between quantum safe networks, i.e. networks that are secured with quantum technologies, and a coherent quantum internet. And when we talk about quantum networks, we kind of talk about all of this jumbled together. And I think we could really benefit from having a kind of a shared language, a shared lexicon from this, so that we can really kind of acknowledge the fact that there is this huge sliding scale, which really does encompass actually kind of an amazingly large technological range and also timescale range, etc. So for me, I just wanted to very quickly focus on the kind of the two ends of the spectrum to some extent. So the first is perhaps these quantum safe networks. So how can we perhaps take today's networks and make them quantum safe? So have them take advantage of quantum technologies. So for me, it actually comes down to maybe two or three things. I think the first is about reducing barriers to entry. Certainly when we look at QKD equipment today, it is extremely bulky, extremely expensive, and extremely complex. It often takes a team of PhDs to set one of these things up from point to point, let alone a network. So certainly that's the focus for KETS, is to reduce that cost and size by making these components really in a standard processing chain, really, production chain. So that's in commercial foundries where really we can leverage the kind of trillions of dollars of investment that have gone into this space. I think the other thing that's really important is that we really do need to work with the ecosystem. So it's not enough to just rock up with a piece of QKD equipment and sort of hand it over to a telecom and expect to have quantum safe networking at home. It's sort of not going to work with that like that. So we really do need to work hard to map, the primitives and protocols and processes that exist within current networks and map them to make them quantum safe, because it needs to be, almost trivial for people to upgrade. And that's because it's really important for us to build solutions that fit in with the underlying ecosystem of networking on more than just a technical level. I think it's really important to acknowledge that we're talking about, highly optimized networks that are not primarily necessarily optimized for security. They're often optimized for cost or performance. And so, you've heard some of the questions around this already. How would we go about doing this in terms of, do we need the same infrastructure, build a new layer? And I think that's not so easy to answer right now. And it's not so easy for equipment manufacturers or end users, but I think it's really important that we get to solutions. The other major point I had on that was around building trust. So these are brand new technologies. It's super hard to ask people to put mission critical data on them right now because they really are unknown. And so I think it's really important that we are working with early adopters to get some real early wins, because that builds trust not only with them, but I think also within the community, and it helps build that kind of momentum that we will need to essentially get these things deployed. And the critical aspect, the flip side of that kind of momentum piece is also about rigor. So, it's really important that we work to develop standards and compliance so that we can really trust the equipment and the solutions that we have. I think it's really critical that we hold ourselves to the same level of rigor, that same accountability as everyone else in the cybersecurity space. And then very briefly, just on the kind of the future coherent networks, I mean, it's clear that there are lots of technical challenges that remain, but perhaps almost the biggest thing for me is I think we need to be a bit clearer on the use cases and benefits, because ultimately the cost of what we're talking about will have to be paid by someone, and that will only happen for me when there's genuine pull by the end user, and that really ultimately comes with genuine usefulness. So I think that's a challenge for us all, that is not just ourselves, but also those end word users, to engage with them to build that common consensus. So yeah, that's all from me. Thanks very much for listening. I look forward to engaging discussion.
Thanks very much, Jake. That was really interesting. That was really interesting perspective. Thank you. And our next speaker this afternoon is Professor Ruth Oulton, Professor of Quantum Photonics here at Bristol.
Thank you, Edmund. My video isn't being shared, but you can see my slides, so that's the most important thing. Oh, here we go. Sorry, I can start now. There we are. Fantastic. Thank you. Right. So I'm a professor of quantum photonics at the University of Bristol, and my real expertise is in solid state quantum devices, doing things like producing single photons and developing quantum memories. And this is kind of, if you like, my sketch of how I think things are going to go. And I'm going to give a fairly hardware perspective, if you like. I think it's going to become really important to divide the sort of cheap small scale from the medium scale to the large scale kind of hardware that we're going to need. And I'll explain what I mean by that in a minute. But the end users are going to be people in the home, and for things like banking and healthcare, for example. And on the other end of the spectrum, we're going to be looking at connecting to National Quantum Computing Centre or other available quantum computers. And actually, I think there's also scope to look at using modified quantum light states for doing all sorts of other things using sensors and metrology and scientific experiments. Next slide, please. So this just explains a little bit about how I see things developing. I mean, what's very clear to me is that Jake was talking about the two ends of the spectrum. That's how I see it as well at the moment. You've got, let's say, single photon or CV QKD, and on the total other end of the spectrum, you've got a quantum computer, and those are very different in terms of its scale. But actually, I think these are going to, in the longer term, come together. What I mean by that is that what you have in your home or at the end user stage will become more and more complex, and we're going to have computing being done in a much more distributed way. One of the things you need to do that is really start to develop realistic and efficient quantum repeaters and quantum memories. Now, the technology for that is still very much under development, and it's really quite a low technology readiness level, but I think it is going to come on. Now, one of the things that will hold back things like quantum memories is that they tend to be using quite unusual materials that need very specific and good additions, particularly low temperatures, cryogenic temperatures. And what I can see is that if you want to make this technology readily available to many end users, you're going to have to take out the cryogenic element of that away from the end user. So how I envisage it is that you'll have things like sort of like a cryogenic substation where quite a lot of the expensive hardware is kept, and very efficient optical interconnects going to an end user. For example, in this little house here, you might have a small photonic chip where it takes as an input, let's say, single photons, and churns out a series of a small bunch of entangled photons, what we call a cluster state. And that can be done because you can do that with a simple room temperature chip. Okay, that might be afforded by some sort of quantum repeater state. It might go to a quantum computing center. And the benefit of this is if you've got entangled states, then you could do blind quantum computing. You're adding security in there as well. And I think it's going to become very important to establish networks of entangled states between lots of different end users. You are going to need probably at some point quantum memories to be able to use that as well, though. So there's got to be a way of communicating quite efficiently with something like a substation. That's going to be very difficult because to establish that network is a big investment, and the sort of user case, I'm not sure is quite there yet. However, I do think that there are applications which need to be, considered. There's some very interesting ideas about using entangled states distributed over very long distances to improve timing and clocks, for example. If you can do that, then you've got more accurate GPS and positioning. That could be a huge benefit if you're the only country that has that, for example. But that really is at idea stage and certainly not well developed. Another thing you can look at is saying, well, we're talking about 6G and the sort of the internet of senses. Well, sensors tend to use light. I think what's going to happen here is that instead of using miniature lasers like we do now, maybe we'll start using modified quantum states of light that are already available if they're in this network. All sorts of things. So any kind of optical sensors, looking at nanotechnology, I could see that being a whole new field. It might start off with early adopters in universities because they might have access to a local area network of these things, but you could see how it could quickly become quite important in something like healthcare, for example. Okay, so that's my vision of, so from a hardware perspective, how things might develop. Thanks, Edmund.
Thank you very much, Ruth. Thank you. For our final speaker of the day, we go to Professor Reza Nejabati, who's going to give us a bit of a networks perspective to complement our earlier talks.
Okay, so sorry, I cannot say that I am not somehow I cannot share my video. It doesn't let me turn on my camera, but I will share my screen.
Thank you.
So hopefully you will be able. Can you, Edmund? Can you see my screen?
Yes, I can see it.
Okay, let me go to full screen mode. So the whole idea is that we need to define what is quantum internet. To me, there are quantum internet made of combination of the three pillars. One is that using the using the non-cloning property of the quantum and to create a quantum security. So you cannot repeat the keys or clone the keys. So that's one way, quantum security. The other is that superposition capability of the quantum states, which at the same time exhibit both 0 and 1 at the same time, creates a powerful capability to create a quantum computers, so which are very powerful. And then the other thing that you can teleport and entangle and teleport information using quantum entanglement and teleportation is another powerful things that you can create a very interesting and powerful networking concept. If you combine all these three together, our quantum internet. So quantum internet is not about creating a network that does security. It's not about creating a network that provide access to computing. It's all above together. I mean, it's like a core network that you whatever you do, essentially you either access the Amazon or Google or somebody's cloud infrastructure or data center. Quantum internet is the same way. Do it securely, access instead of the normal computing power, a quantum computing, quantum data center, and do it with the very advanced network called entanglement and using entanglement and teleportation. Now, if you want to do a reality check on this, so to achieve that, you need to create a dynamic quantum network, not only do the security, but also do the quantum information transmission generally. So that would be create an infrastructure, a network that basically you can achieve the concept of the cloud quantum computing plus quantum security. So meaning that you have a quantum computing power access to everybody in internet and also secure using quantum security. However, there are several big challenges to address. First of all, how you want to switch quantum information or qubits. Essentially, we call qubits an entity that transmit quantum information. So how we want to switch them, how we want to move them around the network, how we want to route them. There is a new set of technology that has to be developed on that. Also, doesn't make a sense that my previous panelists, they say that to create a dedicated infrastructure for your quantum, either satellite or terrestrial. So you need to try to find a way to coexist with the existing internet infrastructure. Your existing optical network infrastructure should be able to support. You need to develop new technology to support the coexistence. And also the whole concept of the multi-party entanglement and entanglement networking, where basically the information from several users are entangled at the quantum level and transmitted are important to develop. Current technology to support these challenges are suitable for QKD or security only. Means that they suffer from a lot of bit error rates, a lot of error rate. They have a low fidelity. But if you want to bring the concept of the really quantum cloud computing and quantum internet in a real term, then you need to have a high fidelity, high reliable network. In my group in University of Bristol, we try to address this. So we have created experimental testbed for that, which we hope that would be a first stepping stone of experimental testbed for quantum internet. First of all, we have a mesh of the fiber network, which is connected to a real application, which is 5G in this case. You have seen the 5G testbed connected to this. And then also, what we have is a fully dynamic, supported dynamic switching of the not only classical, but also quantum information, quantum channels or qubits. We developed a specific switching technology for that based on quantum ROADM technology. It supports coexistence of the classical and quantum channel. And we achieved this using very complex AI-based algorithm, machine learning techniques. We use machine learning techniques to basically put the quantum and classical channel in the same fiber together. Also, we are working with the pioneering quantum computing industries to create to equip our classical computers, which is in this case edge computing, with a small quantum processor, few qubit processor. We call it quantum computing accelerator or coprocessor, to be able to do a specific task at quantum computing level and help the classical computers. So we have created this and we basically testing what are the challenges for doing the dynamic networking to support both quantum computing and quantum security for next generation of the network applications. with this, I conclude my 5 minutes. Yeah.
Fantastic. Thank you very much, Reza. And thank you very much to all our panelists for giving us a quick overview of their vision of what the quantum internet might look like. To make our discussion concrete, I think it might be quite useful if we just talk about we look at this fundamental question: will the Smart Internet Conference in 10 years' time be delivered over the quantum internet? And I wonder if we could quickly just go around our panelists just to see what their take on it is. From Jake, from somebody who's making the sort of kit to do that, do you think that's the case?
Jake,
I think we're having
Oh, hello, can you hear me? Sorry.
We can hear you perfectly. We can hear you perfectly.
That was the perfect time that Zoom decided to boot me off the call. Apologies.
Of course.
So, yeah, sorry, just to kind of quickly answer that question. I think in terms of a quantum safe internet, I would say it's, for me, it's very high probability that at least some core part of what we will be doing will be secured. So when you think about the infrastructure that say Zoom uses, then you're talking data centers, the backbone, metro networks. All of these things seem like they will be prime areas. Whether we'll quite have end-to-end in the home, I think that's more unlikely. It's possible, of course, but I think it's unlikely. I think in terms of a larger sort of coherent quantum internet, no. And if anyone does think yes, great. But I would ask you, why would you want to?
Thank you. That's really thought-provoking. I wonder if we could go to Ruth on from a devices perspective.
Yeah, I think I broadly agree with Jake. I think to some extent there will be some kind of quantum security. I personally think, it's very likely that sort of local area people in our local area will be able to connect in with a completely quantum secure network. I think possibly even nationally we might have a fledgling network with quantum repeaters in place in 10 years' time. Probably be an atomic based one. Doesn't mean though that the full quantum internet will be there, because I think the capability to add in all these very complicated elements like quantum memories and repeaters at scale is going to be very challenging, even in 10 years' time.
That's thank you, Ruth. I wonder what the our networks colleagues, George and Reza, would make of that. George, would you like to go first?
Definitely. So I totally agree with both Jake and Ruth. The reason is, just to extend what Jake said, the question would be, do you think that quantum computers will be there in large scale? In that scale, so that they are distributed and you will need to interconnect them in 10 years' time. So I really doubt. So in that sense, quantum internet with a broad sense doesn't seem to be a real life deployment case for the next few years. That doesn't mean that I really feel that the prospect is in that direction. And as Jake said previously, your investment has to make some sense in generating money. And I think that quantum computing is actually the best case that one can make in order to justify the sort of investments that are needed. So eventually we will see the quantum internet, and we will see that connecting quantum computers around the world. But I don't think that it is realistic to say that this is going to happen in the near future.
Fantastic. And Reza, do you want to add a couple of words?
Yes, I want to go completely different from the other panelists. As I define quantum internet, is quantum computing plus quantum security. No, if even quantum security, even now we can implement it. I mean, no, even in a year time or a few years time, I mean, we are not using the KETS equipment to do a national quantum security. I mean, they have a fantastic technology and we can do that. Now, the question is that is quantum security is dominant security solution in the net for even next in Smart Internet Lab? I put a question mark because there are post-quantum security. I mean, there are quantum safe approach, which wouldn't be based on the quantum security. And I personally have my own question mark if quantum security would be a dominant security, even if technologically it's possible, we can do it today. Now, in terms of the quantum computing, if you think about in a few years' time, even not 10 years, I believe that quantum computing would be cheaply, when I say cheaply, not for home user, but cheaply available at the corporate level, possible to purchase. But you ask the question, if we deliver quantum, a Smart Internet Lab conference over quantum internet, but okay, for security, I understand, but for the computing, what we need, I mean, if you think about the computing processes used for the Smart Internet Lab delivery is image processing, the only thing we do, and image processing and streaming. And quantum computers are not general processors. They are processors for specific processes. So I don't think they are going to be used for image processing. And therefore, I think they will be available. They would be a technology to network them, but I don't think they would be useful for delivering the quantum for a Smart Internet Lab conference. That's my view.
Thanks very much, Reza. And in fact, the panel sort of come on to one of the questions we've had from the audience, which is Hilary Frank, who's asking, do you foresee the quantum internet as eventual replacement for the traditional mainstream internet, or to run side by side as an alternative to that mainstream internet? And it sounds as if, certainly from the feeling of the panel, is this is very much something which is going to be part of an ecosystem. George,
in coexistence. Yes, you are right. Yes, part of ecosystem.
There's sort of coexistence between
the two will have to coexist, and the fact is that they will be addressing different needs. So definitely, the quantum internet is not going to come as a replacement to the classical internet. So you won't see classical information exchange over quantum data. That would be expensive and without a particular justification for doing so. I think that they will have to coexist because this is what makes sense from the implementation point of view, and there's no replacement because they target totally different applications.
Excellent. And actually, this is a question I think is perhaps for some members of the panel. Alex has got a question about this, which is, do you think that the quantum cooling issues will require water cooling for some sort of advanced cooling mechanisms or cryostats? And I wonder, Ruth, if you'd like to give us a perspective on that.
I think water cooling isn't going to cut it, I'm afraid. I think it's going to be much more sophisticated cryogenic cooling, probably with liquid helium. And it really depends on the technology is how cold you need to go. So with the best, with the best hope is we get to liquid nitrogen temperature, which is 77 Kelvin, which is much better than liquid helium temperature, about 4 Kelvin. Some applications use micro Kelvin, which require really, really expensive power-hungry fridges. The only thing I'll say is that many of the applications don't require active cooling. Once you cool them down, they're like, they're like a thermos flask. They don't generate huge amounts of energy, we hope, or at least you need to design it so it doesn't generate huge amounts of heat. So it should hopefully, once you've got that system working, it can contain a lot of qubits, if you like, and shouldn't be too energy consuming. So that's let's say for a substation, rather for a quantum computer, it's a completely different ball game. Of course, there'll be huge cryogenic complications there, I think.
Fantastic, thank you. Sorry, Reza, did you want to?
Yes, I want to say. I mean, that there are academically there are solutions are being proposed that on the computing side they don't need a cryogenic cooling. And I have seen the startup are also being formed, the technology startup that looking at the quantum computers that are room temperature operating. So I don't know, I am not that that familiar the physics of it, but there are solutions being provided to overcome, at least on computing side, on the cryogenic cooling system. Yeah.
In some ways, the most interesting thing is, as Ruth was talking about, moving the cryogenics to somewhere central where it can be provided almost cryogenics as a service in like a central thing.
Yeah.
And that's, which is, sorry, Ruth.
I was just going to say that I think even though there might be approaches which don't require a lot of cryogenics, it'll feature somewhere because of just the fundamental physics of the problem. So if you can reduce the amount of cryogenics you need, that's your most important kind of engineering principle, I think.
I agree.
Fantastic. And in fact, there's a follow-up question to, not follow-up, in fact, it came beforehand, but I think it's very relevant, which is from Zoe Davidson, who's asking about this idea of energy efficiency and sustainability. And is that an active research area in the world of the quantum internet or not at the moment?
Maybe I can jump
Please
in.
go.
I would say that sort of from the very highest level, like the 90% of the answer probably is no, and it probably should be. But what I would say is that I think when you look at the potential markets that, for example, that we are looking at, energy consumption is a huge deal. It can be a make or break because of cost. So whilst that certainly is not by any means the be all and end all of sustainability, clearly, manufacturing processes in terms of impact on the environment, use of energy, etc., is a really important aspect of that. I think there are some market forces in play such that, for us, when we're looking to miniaturize devices such that they can live in a data center, it almost is a prerequisite that they need to be low, not only low cost, clearly, but they need to be low power, because low power means low cost, because that indeed is often what a lot of the money and running costs is spent on. So for us, that's a kind of a nice byproduct of integrated approaches. They tend to be a little bit more power efficient.
Fantastic, thank you. It's and actually this is sort of following on from this sort of idea of sustainability, this sort of broader idea that George was talking about an ecosystem of computation. And I wonder if we can take two questions together, if that's okay. David is asking, will the wide-scale deployment of quantum networks be driven by breaking traditional encryption? And Dr. Nejabati is saying, what do you think the role of post-quantum cryptography in the quantum internet is? And I think these are two different perspectives on the same very important theme, really. What's the use case for the quantum internet? Is it there? George, I wonder if you want to say something about this.
Yes. Absolutely. So let me start with the post-quantum. Recently, NCSC has announced that they have a post-quantum solution. It's credible, but everything comes again to energy consumption and deployment. I think that in the near future, post-quantum will have again to complement QKD, in the sense that, for example, post-quantum will be used for authentication, which is an issue that QKD cannot sufficiently address, and QKD will actually be used in order to distribute through quantum keys. And that's my personal take on post-quantum. Of course, as I said, it will all break down to the deployment specific. So, what are the power consumption, for example, or on the processing required for the post-quantum versus what QKD can do in the future, for example, with miniaturized equipment and integrated technologies. Now, with respect to the use case of quantum computers, I don't think that these are so breaking the encryption is obviously one of the use cases, but I don't think that they focus on that only. I think that one of the biggest cases is simulation of very complex systems. They fit very well with AI algorithms and neuromorphic. So I think that a main part will come from these productive processes rather than the destructive breaking of encryption systems.
So you think the market pull is much more towards things that could be solved rather than things that could be broken?
Yeah, simulations for pharmaceutical purposes, for environment, etc. I think that these have been traditionally been the driving motivation behind any progress that we've made.
Absolutely. Ruth, I wondered if you wanted to talk a bit more about the sort of simulation aspect of it, or any other.
Yeah, well, I guess, yeah, so I think you want to kind of think about these quantum computers as a special type of supercomputer, really, and you're going to be addressing all the kind of questions that they attempt to address. And of course, supercomputers are very good for one thing, but not particularly for other things. I still don't think we know exactly what these computers are going to be capable of, but I'm sure that there will be a wide variety of applications as soon as they start becoming online and available. It's why it's really important to make them available to a wide variety of users, so that we can actually kind of find out their best use cases, actually.
Absolutely. I almost wonder if it makes sense in some ways, in the same way that we now think about the computer as being part of the network, not having that clear dividing line. I wonder if the quantum internet is going to go in the same way, that we see it all as part of a sort of holistic ecosystem.
Yeah, that's possible. It's a very difficult to know, really. Yeah.
Reza, I can see you've got something you want to add.
No particularly, but yes, will be at the moment. If you go to Amazon Web Services, you can get a service on quantum computing simulation, but it's a simulation of the quantum circuit. But you can buy a quantum computing capability, and that's where Amazon is going. And in the near future, they are going to have a quantum computer that you can rent it out. So that would be a same way that you go and buy a web hosting server. Now you're going to go and rent a quantum computer and run your algorithm. That's going to happen. I mean, but if that happens, then the way to scale it is various way. Monolithically, they don't scale. They very well the quantum computer for various physical reasons. But then there are other way to scale them. For example, putting around the network or connect them in distributed way. That's one thing to go. And then really something that I want to mention is that we need to, quantum internet is not about security. I mean, there are major doubts about at the government level about the security validation of the quantum, because at the end of the day, even if you deploy it for energy, for whatever reason, you secure your link. And if you look at the security report of the various security agencies, the point-to-point link is the bottom of the list. I mean, there are other problems in the point of attack, if you like, in your security, in your stack for security attacks, which is the link becomes the very, very bottom. So I think that what we do with doing the research on quantum security and quantum network that support quantum security dynamically, we are slowly developing the capability to do the quantum information networking. Once you have that, then you can choose to use it for security or for just connecting the quantum computers. I think it's a little bit of the limiting if you say everything is about security. Is a very, very big doubt if security will be the killer application for quantum communication. Yeah.
I see. Fantastic. And I'd just like to take the opportunity to just look at some of the questions in the chat. I just wondered if we could broaden the discussion just a bit beyond. We've talked a lot about quantum computers and about the quantum internet and how it might be. A couple of people have asked, I can see Neil and Alex have both asked about what one might call the ancillary technologies that surround this. So about Li-Fi, for example, or about 5G, and how that would interact with the sort of the backbone, as it were, of the quantum system. I'm not sure if Jake, if you've got anything you wanted to say about.
Sure. I think it's so yeah. I mean, the question around sort of RF links and Wi-Fi is all kind of really around access, and particularly, or at least that's the way that I see it, is often framed that way. And you know, from a fundamental physics point of view, there's nothing stopping you doing this, right? I mean, I think it's clear that you know, it's possible to make coherent quantum states using RF and indeed certainly Wi-Fi. Really, the question then is really an open one for me. Is actually, you know, let's take as read for a second that maybe you have a QKD network, quantum repeaters, and all the rest. Where actually is it beneficial to get your quantum information to? Actually, is it beneficial to really get it to your laptop, or perhaps your router in your home? Perhaps even in Reza's vision of the future of a quantum internet. I mean, I don't speak qubit. I speak in classical information.
Yeah.
And so there needs to be an interface between classical communication and the kind of the quantum states. And I sort of question, do I actually care whether that's on my computer or in a router? And the reason to say that is that, I mean, if you look at Europe, there's a large, well, and increasingly here, right, we have fiber to the home. So it may be that, you know, I guess I'm sitting on the fence very unhelpfully. I could totally see that we might want those links right to our devices, but actually, in terms of the quantum links, it may be that it's not necessary, and actually we can live and indeed prosper with those direct links. Yeah.
Sorry, I was muted myself there. The just to sort of follow on from this idea about fiber to the home, Rana's asked in the chat about the backbone optical fiber for these, and he says, could you please put some light on the advantage of hollow core fiber use to support these end-to-end quantum infrastructure in a terrestrial scenario? I don't know, George, perhaps you're the best person to come in on this.
Yes, we've recently experimented on the hollow core fiber, and it proved what we expected, that they are far more resilient, if you like, in transporting your quantum and classical information all together. That's because the optical signals propagate in the air, so they do not experience any non-linearities, and therefore we can avoid the Raman phenomena or four-wave mixing phenomena that would otherwise generate, you know, photons on the quantum channel and therefore impair their performance. So the question with the hollow core is whether they will manage to produce it, you know, at the lengths and the levels of SMF, and whether will that replace the SMF. It's really a very costly process to duct a new fiber all over the place, or will that be applied in particular applications, such as, for example, again, considering it as a quantum interconnect in interconnecting your quantum computers, or other specific applications that may come into place. The other advantage that hollow core has is the fact that because it propagates again in the air, this is a low latency compared to SMF, so that can be bonded well with reduced latency requirements in applications in supercomputing, etc.
Thank you. Ruth, I wondered if you wanted to add anything about the sort of challenges of fiber to device linkage or interconnects, I suppose.
Yeah, so obviously everybody is worried about losses through the fiber. What worries me is the losses at the interface between your device and fiber. That is still a problem which has not been solved, even, you know, for classical devices where it's not so important. Here it's really, really crucial. Most of your losses are between your device and the fiber before it starts propagating. So that is, I think that's a solvable problem, but it really does need a lot of attention now if we're going to make these systems successful. Whether hollow core fiber or standard SMF is better remains to be seen. I think there are good reasons to argue for both. Depends on the device as well.
Fantastic, thank you. Excellent. And just, I'd like to finish off because we're heading the last few minutes of our discussion. I'd like to get the panel's opinion about the next 2 years and the next 10 years. I'd like to know what the most exciting developments are going to be as we move into the next, that's looking at focusing on those 2 time periods. And I wonder, Jake, if you'd like to start us off on that.
Sure. So I think for me, perhaps the most exciting thing in the next 2 years is that we're really now starting to see, wide scale deployment of test networks. I mean, the EuroQCI network, I think, is a huge deal, where we'll really be able to test the use cases of QKD on a much larger scale than we ever have before. And then I think longer term, looking at QKD, I think SAT communications, if we can get those to essentially become essentially global coverage, then we'll really put the capability of QKD sort of on par with what our current networks do today. And I think that's a thing that's often missed, is that it's very easy today for me to get an internet connection to Australia, and often that is kind of business critical for people. So when that becomes technologically possible, I think that could be really, really very exciting.
Fantastic, thank you. Reza, I wonder if you want to tell us about what you're excited about this next 2 years and the next 10 years.
Well, I think what we see, you have seen the 5G being deployed. Now everybody think about 6G. I believe in next 2 years, we will see that a standardization of the 6G will coming out. I mean, become a standardized for the industry to start to develop the technology. And I believe in 6G, quantum computing and security both have and in fact, post-quantum security both have a significant place, and they will feature in the basically a standardization as a feature of the 6G network. That would be in the next 2 years for me most exciting things that we'll see that in the standardization will come out. And in 10 years time, my belief is that we will see that the like of Amazon and Google will offer to their customer some sort of quantum computing capability as a service, either as a co-processor or as an accelerator, but some sort of quantum computing would be offered to the public as a service. So with some sort of application service on top of that. Yeah.
Excellent. George, what about you? What's the most exciting thing for the next couple of years?
I'd like to quote our previous colleagues here in the University of Bristol and see quantum in getting a huge amount of funding towards the 1 million qubit quantum computer. And I guess that if that becomes a reality, then we're on. The very exciting part of it is that these quantum computers, in comparison to all other solutions, is a photonic one. So qubits are coming in photons in the first place. That makes the communication aspects easier. So I would very much look into these sort of directions. Of course, they are competing with superconducting quantum computing options. There are so many competing technologies that yet to evolve in the next few years. So I think that this is going to be the developments in that area will be very exciting for the quantum communications as well.
Fantastic, thank you. And I wonder, Ruth, if you'd like just to set out what you see in the next 2 years, the next 10 years, what's the most exciting development that's coming in the pipeline?
So I think in the next 2 years, what's going to be happening in quantum computing is that we're really going to start seeing these computers start to produce calculations or simulations that are actually cannot be done with classical computers. I think we'll start to see that within the next couple of years. Actually, it's really taking off now, and that will give us a good reason to connect to these things in terms of quantum network. In the next 10 years, what I would like to see, and I don't know if it will happen or not, what I would like to see is, I think A lot of focus previously has been on either QKD or quantum computing. I think we need to focus more on sensing and metrology. I think really working out what all the exciting things we can do firstly from physics and then an engineering perspective when we start to distribute entangled states, because that's going to give us a reason to actually build these large-scale networks that isn't about security. It's about doing interesting new, seeing physical phenomena and utilizing that physical phenomena for real applications. I think that's going to be the future in 10 years.
Brilliant. Thank you very much. And I'd like to take the opportunity to thank both our panel and our audience for coming up with great questions for them. And thank you very much for your detailed and thoughtful responses. It's been really exciting to be able to come to it. Thank you. The only other thing to add is, after we thanked our panelists, is to say that there's now going to be a networking session on Remo to finish the day. So I'm going to be heading there for a bit, and of course I hope to see everybody. I hope to get to meet some of the people that we've been talking to this afternoon. Thank you all very much.
Bye. We'll see you in the Remo.
I'll see you in the Remo.
Thank you. Bye. See you in Remo.
Bye.